400 gig is finally here. At Prolabs, we're very excited about this new technology, but we also recognize that careful consideration is required for a successful migration to 400 gig. Now I'd like to introduce our very own global product line manager, Ray Hagan, who's going to give you a full walkthrough of 400 gig architectures and everything you need to know about them.
Hi, my name is Ray Hagan. I'm the global product line manager for Prolabs. We're here today to talk about 400 gig architectures and what you need to know as you deploy 400 gig. Our agenda today is to discuss, a few key themes. Our foundations, where we talk about modulation, form factors, interfaces, connectors, things that are really critical to deploying 400 gig. We look forward to that, applying that to real-world networks in data centers and service providers. How are the real practical things you need to know as you deploy 400 gig? And we'll also talk a bit about what's beyond 400 gig, what lies beyond. So we look to our 400 gig foundations, and here's where we really want to talk about hows and the whys of why things developed the way they did, and what does that mean to you. So as the 400 gig standards were developing, there was quite frankly a lot of competing standards at work. So there were things like optical standards. How are those going to work out? There were, how's this going to roll down to 100 gig? Then also, what form factors would be used for 400 gig transceivers? OSFP, QSFP, DD, even mu QSFP, DSFP, SFP, DD, CFP8 were all standards that were in the queue, ready to go for 400 gig. And then to take that kind of alphabet soup, if you will, to the next level, there's a whole host of new connector types that will also be introduced with 400 gigs. So you've got your MPO12, MPO16, your standard duplex LC, and a new CS connector that were all introduced that really add a lot of complexity to a 400 gig deployment. So if we look at our 400 gig foundations and form factors, there were really three form factors that bubbled to the top that switches were developed around: CFP8, the OSFP, and the QSFP56DD connector. The real differences here, what really is in the power and the heat and thermal management, if you will. QSFP56DD uses a little less power, has an indirect thermal management, meaning that it's a little more advantageous for the switch providers, or when they're developing switches and routers around these transceivers, to be able to utilize the same thermal management components they use for the QSFP28 100 gig technology. So hence the QSFP56DD. Otherwise, we're going to be calling it moving forward here as the QSFP-DD form factor has been, crowned, if you will, as the winner of the form factor battle, if there is such a battle. The other two form factors perhaps are not going away. I think there's going to be a market for these as we look to beyond 400 gig. But right now, this is going to be the QSFP56DD is the winner, if you will. So even though we think we had a clear winner within that QSFP DD form factor, there's still some variation, if you will. There are actually three different hardware types: Type 1, Type 2, and Type 2A. The Type 2 transceiver is perhaps the most commonly deployed today. I think the real difference there is just the size. It protrudes a bit further out from the faceplate than the Type 1. The Type 1 is a little closer in size to the standard QSFP28 100 gig transceiver. And to probably oversimplify the reasons why, it just, you need to put more components into a package. You may need a little bit extra space there. The Type 2A is a newer addition to it to take care of thermal management. I believe that's going to be in relation to upcoming 400 gig ZR things down the road. So it needs a heat sink on the top of it to take care of the thermal management down the road. On top of that, there is a common management information system used with these transceivers, and this believe it or not, there are two revisions of this out there in the market today. And quite frankly, if you're a consumer of 400 gig transceivers to deploying your switches and routers and other network elements, you don't really need to worry about this a whole lot. I think where it's going to come into play for you is where you're consuming your technology. If you're buying from a third-party supplier, you may need to ask the question: which CMIS are you using? And make sure that's the same CMIS that your OEM is using. So then we move on to modulation. And PAM4 modulation is perhaps the biggest change here with 400 gig that networks are going to find opposed to, the 100 gig migration a few years ago. So PAM4 is a generational shift in optical networking. It has far-reaching impact, far beyond 400 gig. It goes all the way to 200 gig and 100 gig. It's going to impact each section of your network once you deploy PAM4. So what does that mean? So from non-return to zero encoding, so that's a one-step, if you will, encoding algorithm, where you're simply going up and down, to a PAM4, which is a four-step, demonstrated here by the graph. And how this is manifested, if you will, is in the optical signal. You can see by the eye diagrams on the right-hand side of the slide that you can see both steps in a NRZ eye diagram on top, and at the bottom you can see all four steps in the PAM4 eye diagram. So again, this is going to be a fundamental shift in how transceivers are deployed for 400 gig, and as you look to due to the applications of the aggregation and breakouts, and how everything rolls from the edge into the core. So we'll get into that, all those in our application section. So where PAM4 has a big impact is on the transceiver interfaces. We've got the available interfaces on the multi-mode side, the SR8, and that uses a new MPO16 connector, a max of 100 meters. On the electrical side, it has 8x50 PAM4 electrical signaling, whereas on the optical side, it also has 8x50 PAM4 optical signaling. And these are eight transmit, 8 receive pairs in that fiber connection. We're moving to the single mode side. We have a couple of MPO type connectors or parallel type modules, transceivers, the DR4 and the DR4 Plus. These transceivers use the MPO12 connector, much like we've accustomed to for breakout connections over the years, but for the 500 meter and 2 kilometer reaches. Now, where things get interesting here is with the FR4 and LR4. These are used duplex LCs, and again, these are still 4x100 optical on the PAM4 side, but these multiplex those 4 lanes onto the single fiber for their connection. All these transceivers are all 8x50 gig PAM4 on the electrical side. So as we look at what's next, right, for these developing 400 gig interfaces, there's a number of them. You've got your PLR4, which is a 4x100 LR, so basically the same as the DR4 and DR4 Plus, except for a 10 kilometer reach. Then you get to SR4.2 on the multi-mode side, which is trying to take the place of a quote-unquote BiDi connection. I'm using the MPO12 type connector, going to have a transmit and receive on a single multi-mode fiber. And this is where OM5 fiber is going to come in handy here for this particular connection. Then there's a few other interfaces that perhaps have actually been around for a while, FR8 and LR8. And the only real difference here, in my opinion, is on the implementation between these and the FR4 and the LR4. On the optical side, you're multiplexing 8 50 gig connections using LAN WDM opposed to CWDM on the other connections. So it's a bit of a implementation change there. But those two interfaces, an FR8 and FR4, obviously are not interoperable. So just something to keep in mind as you're deploying your transceiver technology. Then you've got the ZR, the 400 gig. Now, this is something you're going to see over the next year come to market. And this is going to be a 1x400 gig coherent DWDM technology. So this is pretty exciting, right? This is where we're going to have real change for long haul networking and beyond, and from the core to the edge. This is going to be a big change over the next year or so. So as we move on, we've got a slide up here with a bunch of 100 gig and 200 gig transceivers. You may say, hey, this is a 400 gig, what you need to know. Why are we talking about 100 gig? Well, that's a really great question. And the real reason why here is that 400 gig is going to be deployed mainly in the core up front and in the main core of the network. So you're going to need to roll up or aggregate or break out to whatever term you want to use your 100 gig connections into that 400 gig. So we talked about PAM4 and networking. Here's where that becomes far reaching into the 100 gig and 200 gig world. So the DR1 FR1 and LR1, these are single wavelength optical technologies, 1x100 PAM4 optically. But on the electrical side, they are all 4x25 NRZ QSFP28 transceivers, meaning that these transceivers can be installed in legacy QSFP28 100 gig switches deployed in the network today, meaning that these transceivers help integrate those legacy switches into your new 400 gig network. So we move on to our 2x100 gig QSFP28DD transceivers. Now, these are a little different transceiver. As you can see by the specs on the slide, they are NRZ both on the copper side or electrical side and on the optical side. So as we get into the applications where these are used, we'll get to understand why someone would want these types of transceivers. And then the final transceiver in the slide here is a dual lambda QSFP28 PAM4 transceiver. And this is a PAM4 dual lambda, means it's two 50 gig DWDM on the same fiber. So this is a different type of transceiver today used in a QSFP28 type environment as well. Now, these single lambda 100 gig QSFP28 transceivers. So these transceivers, as we mentioned, these are really critical in integrating legacy 100 gig infrastructure into the new 400 gig network. Now, what makes these a little different is inside the transceiver, there's a gearbox. And in this gearbox, it does the retiming from 1x100 PAM4 to 4x25 NRZ. And that retiming is critical to making it interoperate with the switch. Now, inside this gearbox is also a DSP. And this DSP contains forward error correction. That forward error correction works with the 400 gig transceiver on the other end without need for FEC or FEC on the host. So FEC is done on both this transceiver and its 400 gig subtender on the other end. Very much something you need to know as you're deploying 400 gig. I like to think of this, and again, I'm probably oversimplifying it, but I look at the 2x100 gig as a two NRZ transceivers in one housing. So let's think about that. Meaning that inside that QSFP28DD transceiver, essentially are two working QSFP28 LR4s or two QSFP28 CWDM4s. So that's an interesting way of looking at it, and that's how helps me rationalize why this matters in the network. Now, how this works, as you can see from the slide there, a QSFP-DD transceiver has two sets of pins. Same pins that work with legacy QSFP28, then a whole other set of almost identical pins on the other side of the piece of the printed circuit board that allow it to essentially work two independent transceivers within one. And when you say that, what do you mean two independent transceivers? Well, this particular transceiver integrates the CS connector. I mentioned that's one of the new connector types. So a CS connector essentially is two transmit and receive fiber cores, if you will, within the space of one LC connector. So those of us who are around for a long time, like myself, we remember when the LC connector came to market and it doubled the density over existing SC connectors, where two LCs, a transmit receive pair, fit in the space of one SC connector. Now, same thing is going on with the CS connector, where one CS connector is fitting into the space of one LC connector. So meaning on the face of this QSFP28DD transceiver, there are two transmit and receive pairs using CS connectors, allowing for this independent operation of 2x100 gig transceivers. The QSFP-DD 200 gig, now these are evolving standards. They use PAM4 and 8x25 gig, 4x50 gig. There's a number of different thoughts out there right now how this is gonna shake out. I think over the next year, we're going to see many more 200 gig transceivers under the market. These are going to be in various PAM4 varieties, but again, still very much developing as of today. So, as we talked about connectors being a big deal with the QSFP28DD connectors, we move on to the rest of the 400 gig transceivers and what connectors do they use. The SR8, as we mentioned, uses the MPO16. It has 8 transmit, 8 receive pairs, as we can see by this slide. The DR4, DR4 Plus, and PLR4 will use the MPO12, and they'll have 4 transmit and receive pairs, very similar to the same scheme used in QSFP Plus and QSFP 28 modules for the last several years. The QSFP DD-FR4 and LR4 again use the duplex LC connect, the standard LC connectors. So let's move on to applications for this 400 gig technology. So this is a standard 100 gig infrastructure data center type of network. You've got your, starting at the core, you've got your data center interconnect, your data center routers, your spine, your leaf, your under row, your top of rack switches, and your servers. Pretty typical, very standard of how today's data centers are architected. So for each segment of the network, from the top of rack, we may have DACs, AOCs, short reach transceivers, to your end of row, you're going to have maybe AOCs or SR4 type transceivers. To your 500 meters, you're going to use either PSM4s or CWDM4s. All the way up to one kilometer, where you have CWDM4s or LR4s, and up to your data center interconnects, where you have your LR4s, ER4s, or even coherent type modules. So this is very basic, very standard data center architecture today. Where things are interesting and make it very easy for the upgrade to 400 gig is that for each step in this network, there's a corresponding 400 gig transceiver type. So for each reach, you're going to have a arrow in the quiver, if you will, for every aspect. So if you're looking to go from the core down, or if you're looking to start at the end of row type switches of 400 gig, wherever your deployment model may be, there's going to be a corresponding transceiver there. So, why that becomes very powerful is you're looking at that gives you the opportunity to upgrade your infrastructure or your data rates by 4 times over existing infrastructure. So to me, that's a very powerful way out of the gate for 400 gig. But let's not forget our 100 gig single wavelength products we mentioned there earlier. They also have a very big role in this 4x100 infrastructure. And service providers, in their service networks, also their architecture may look a little bit different. They may have 400 gig in the core. They push 100 gig to the edge and maybe 10 gig to the access, or maybe 25 gig to the access network. But again, a very similar model where they're going to be aggregating from the access network inward. They're going to need a way to roll up that bandwidth up to take advantage of the new 400 gig core. So as you're deploying 400 gig, there's a few things to keep in mind with the breakouts or your aggregation or your whatever you want to call it. So the 400 gig to 4x100 gig breakout architecture really does require some thoughtful planning, across the entire physical layer. Consider interoperability. So currently deployed 100 gig CWDM4 and LR4, so NRZ modulated transceivers, they're not interoperable with PAM4 400 gig interfaces. That's a very big point to keep in mind. Your fiber cabling considerations, so the new connectors, CS, MPO16, you probably don't have those in your network today. You're going to need to buy those, right? You may need to clean them. You may need to do a number of things that you don't do today. So also 200 gig to 2x100 gig breakouts do offer backwards interoperability, meaning that the NRZ modulation makes those interoperable with legacy LR4 and CWDM4 transceivers that may be in your network today. So the fiber cabling considerations there, you may need to worry about new duplex CS connectors, and you may need conversion media. Well, our first architecture we're going to look at here is just a 4x100 breakout, 500 meters. So you may have a DR4 transceiver at the switch or network element, and you'll break those out with an MPO breakout cable. You'll go to 4 100 gig switches, pretty straightforward. Each one of those switches will have a DR1 transceiver. So a DR4 to 4 DR1 transceivers, pretty basic breakout. And we stretch that to 2 kilometers. The transceiver at the network element at the 400 gig network element, it'll be a DR4 plus transceiver. You may also refer to this as a 4x100 FR1 transceiver, depending upon who you're talking to. Now the MPO breakout from there will go to 4 FR1 transceivers at 4 100 gig switches. Now where this is, where this thing gets a little, not quite as straightforward as the previous slide is that you would think the FR1 transceivers would subtend off of the FR4 transceiver. Well, that's not the case. The FR4 transceiver is a duplex LC transceiver with 4 CWDM multiplexed lanes, which quite frankly are not interoperable with each lane on a FR1 transceiver. So a little bit of misnomer there in terms of how standards have worked in the past, but hey, it is what it is. Now, as we look at the 2x100 gig breakout, I promised earlier we talk about why a customer or a network may want to do this, and a couple of reasons why. They may have a very large and embedded base of LR4 CWDM4 transceivers in their network. They don't want to train thousands of installers of which transceiver to use for which deployment. So that's a pretty valid use case there. The key thing here is that the QSFP 28DD 2x100 transceivers will be installed in a standard QSFP DD switch port, meaning that within the same switch, you could have some of these transceivers right next to a regular 400 gig QSFP DD transceiver. So that QSFP DD slot offers a lot of flexibility, and this is one of the key things it can offer. So coming off of that QSFP 28DD transceiver, you'd have 2 CS patch cables or duplex CS patch cables. On the other end, maybe an LC connector that you would connect to a patch panel or maybe even directly to another transceiver. Then the other end, you'd have an LR4 type transceiver in this scenario with accepting it on an LC basis. So 1 QSFP 28DD transceiver on one end, 2 QSFP 28LR4 transceivers on the other end. And if we go down to 2 kilometers with the CWDM4, same exact deployment scenario here. So a little bit of a summary chart here in terms of what's required from a connectivity standpoint for these scenarios. The DR4, you have a single mode MPO12 on one end, 4x single mode LC duplex in the other, just like we've done breakout connections for a long time. With the SR8 transceiver on the PAM4 side, I think the real issue here is going to be the 50 gig transceivers on the far end. Those transceivers probably aren't really available very rapidly in the market right now. It's going to be a while before you're going to have a PAM4 transceiver on optically 50 gig on one end with either NRZ or PAM4 on the copper side. So it's going to be a little while before those transceivers are readily available to perform those sorts of breakouts. On the 200 gig, 2x100 side, you're going to need CWDM4 and LR4 side. You'll need, for each transceiver, you need 2 patch cables with duplex CS on one end and probably duplex LC on the other. There's also an SR4 2x100 gig transceiver also that uses an MPO24 connector. And that you'd use same MPO24 connector that's been used for quite some time. And that will have a little different implementation than what's been used in the past, where you're only using the center, you're only using the outer lanes, and with the middle lanes being not used, going to LCs on the other end. So that's something else to keep in mind. Let's explore this physical aspect we just spoke about. So those MPO to LC patch cables we mentioned. So standard breakout cables, the same sorts of breakout cables we've used for years, with an MPO on one end. So you need a female connector without pins that connect directly into the transceiver. On the LC end, it'll just be a standard paired LCs available both in multi-mode and single mode. For the DR4 and DR4 Plus and the PLR4, you'd have an MPO12. And then for the SR8, should that day come, MPO16. Now, if you're doing the 2x100 gig transceiver, here you'll need a a simple patch cable, duplex CS to duplex LC. Pretty straightforward, 2 patch cables per transceiver. So some of the pros here, it's pretty intuitive, just to patch from network element to network element. Pretty straightforward, even if you have a patch panel in between. Pretty straightforward. They don't use rack space if you're just going direct connects between element to element. Cons, I think your complexities grow. You're talking about things like breakout links. If you're going for a 400 gig transceiver, where are your 100 gig transceivers? Are they right next to each other? Are they in the same rack? Are they in the same row? Or are they in different rows? At that point, you're talking about things like breakout links. How do we engineer those? A number of different things to keep in mind with that sort of deployment. And quite frankly, when you're direct connecting network elements, you're reducing flexibility. You're flexing your patching down the road. So, that's just a standard trade-off over the years for direct connecting versus cross-connecting, right? Is simply you're reducing some flexibility down the road. So another option you may have is on your breakout cassettes. So on the rear of the cassette, we'll take your MPO connector. You'll have 100 gigs off that, say, the DR4 or DR4 Plus or whichever transceiver that we broke out to LC pairs on the front of the cassette that you can tap into your 100 gig pairs. This is both the multi-mode and single mode options. There's capacity for 3 4-by breakouts within one cassette. So a lot of the pros with this is it offers takes care of some of those cons from the direct connection scenario. You can have standard cable links for cassettes at the top of rack. You can run trunk cables between end of row to each rack. Very much very slick in that regard. You increase your flexibility in port and cable management. Some of the cons. So one thing you have to deal with is MPO polarity, and MPO polarity would seem to be straightforward, but most people end up asking, oh gosh, scratching their head, right? Which polarity do I need? Which cables do I need? Do I need crossover? Do I need straight through connectors? And the answer is all depends. All depends on what you're trying to connect. So that's definitely adds to some of the complexities of deploying cassettes. And it does take up rack space where you're using, either a 5-inch LGX footprint or a 4-inch more high density type footprint. So it does take up rack space in your deployment. So as we look ahead, what's the road ahead lies for 400 gigs? So at Prolabs, right now we're seeing that 400 gig network elements, switches, and routers are being shipped by OEMs. They're starting to be shipped after a few years and wondering when's the shipment's going to start, when are they going to start? Well, now they're happening, right? They're shipping this product out to networks, data centers, service providers around the world. So that's good to see. It's good to see in the market that's happening. Now, over the next few months, we're going to see, supply is going to mature, technology is going to mature, the software is going to support more transceivers in the field. So we're going to see that technology really start to mature here over the next few months towards the promise of 400 gig is going to be delivered in network elements delivered by the OEMs. And by the end of the year, we're really going to see more OEMs offering these switches, a much more robust market to buy 400 gig switches, if you will. But then, as we get to OEM, 400 gig is here, it's real. We're going to have real conversations about 800 gig and what's that going to mean to our networks starting probably February of next year at OFC. So there's going to be a number of different things to come their way, but 400 gig is going to be around for a long time. It's going to be a very big shift in the network architecture. I think the internet is seeing unprecedented growth, and we need to shore up the core of the network. So 400 gig will be here forever.
Thank you so much for watching this video. For more info on 400 gig and 400 gig products, the appropriate links are down below. If you like these in-depth explainers like this one, let us know in the comments and make sure to subscribe to the channel for more educational videos like this one. Thanks again and stay connected for the next video.